All right, hi you guys. I'm going to break this up into a couple videos to go through implicit differentiation. I know this is a tough lesson, so I think it might be helpful for you guys to have videos to reference of me working through the examples that we did in class, but also I think I might add a few more basic examples. So before we really start talking about what implicit differentiation is, I would like to remind you of our review of functions from the beginning of the year. And I gave you guys these two equations at the beginning of the year. So y equals to x squared versus y squared equals to x. Okay, and we talked about how not all equations necessarily represent functions. If we remember the definition of a function, the intuitive definition is that every input corresponds to exactly one output, meaning every x value corresponds to exactly one y value. So if we look at the first equation, y equals to x squared, which you guys are really familiar with and know that that's the graph of y equals x squared is a parabola that opens up, and you know that it does represent a function. But let's think about letting x equal to 4. So in this first equation, if we substitute 4 in for x, we would get y equals to 16. So a point that lies on the graph of y equals to x squared is the point 4, 16. Where if we come over to the equation on the right side, so y squared equals to x. So let's let x equal to 4 in this case. Well, if we're solving for y, we would get y is equal to plus or minus 2. So x equals to 4 corresponds to y equals to positive 2 and y equals to negative 2. So two different points. Both of those are points that lie on the graph of y squared equals to x. And the graph of y squared equals to x is actually a sideways parabola. Ooh. Let's try that again. So it's a sideways parabola. And we can see that that sideways parabola would not pass the vertical line test, meaning it is not a function. So if we thought of this as x equals to 4, we would have this point down here, which would be 4, negative 2, and then this point up here, which would be 4, 2. So notice how the equation on the left that we know represents a function, right? It represents the parabola that opens up and would pass the vertical line test. But notice in that equation how y is by itself on one side of the equation. If we come back over to the equation on the right-hand side, and we try and isolate y on one side of the equation, we would get y is equal to plus or minus the square root of x. So if you think about, like, if you were to try and graph y squared equals to x in your graphing calculator, you know how there's the y equals button? You have y sub 1, y sub 2, y sub 3, so you can graph different equations. We would actually, to graph y squared equals to x, have to put in equations in two lines. So you would have to do like y sub 1, so this would be in the graphing calculator. So y sub 1 would be equal to the square root of x, and then y sub 2 would be equal to the negative square root of x. Now, if we wanted to find the derivative, so dy over dx, of the equation on the left. So if y equals to x squared, that's easy, right? You guys know how to do that. Dy over dx would be equal to 2x. And that equation will allow you to calculate the slope of the tangent line at any point on the graph of y equals to x squared. But for the equation on the right, y squared equals to x, how would you go about finding the slope of the tangent line at any point? How would you find the derivative of y squared equals to x? We can see down here when we get y equals to plus or minus the square root of x, that y cannot be defined explicitly in terms of x, which basically means we cannot get y by itself on one side of the equation and have it be defined in terms of x as one equation. So left side function, right side not a function, which makes finding the derivative of the equation that does not represent a function a little tricky. So to actually find the derivative of the equation on the right-hand side, y squared equals to x, we have to use what we call implicit differentiation. Okay, so this is just a summary of what we've done up to this point. So to find the derivative of any given function, we've been able to use these different rules to help us find the derivative of a function, dy over dx. But all those were explicit functions where y was defined explicitly in terms of x, just meaning we could get y by itself on one side of the equation. So here's another equation that does not represent a function. So x squared plus y squared equal to 1. It's actually, the graph of that equation is a circle centered at the origin that has a radius of 1. Do my best attempt at a circle. Yeah, it does not look like it's centered at the origin, but that'll do. Okay, so we can see that, this graph would not pass the vertical line test. X squared plus y squared equals to 1. We can see graphically that is not a function. If we take the equation and try and solve for y, we'd get y squared equals to 1 minus x squared, and then y equals to plus or minus the square root of 1 minus x squared. So we ran into the same issue that we did with y squared equals to x. We get two different equations now, or two different functions that represent the graph of the equation x squared plus y squared equals to 1. So we would have y equals to the square root of 1 minus x squared, and we have y equals to the negative square root of 1 minus x squared. Okay, one equation represents the top of the circle, and then one equation represents the bottom of the circle. So we say that y is defined implicitly, basically meaning we cannot get y by itself on one side of the equation. So if we want to be able to find the derivative, dy over dx, for this equation where y is defined implicitly, we have to use implicit differentiation. Okay, and to do this, we're going to be thinking about differentiating each side of the given equation with respect to x in hopes of finding dy over dx. So if we take that equation of the circle that's centered at the origin and has a radius of 1, our first step is going to be to show that we're taking the derivative with respect to x of each side of the equation. Okay, so with this step, we know from studying derivatives before that if we're taking the derivative of a sum or a difference, you can take the derivative of each term in that sum or difference. So we're going to take the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And then we still are taking the derivative with respect to x of 1. Now, to actually take the derivative of each term, I want us to think chain rule. So I actually want us to think about there being parentheses around the x and the y, so that we're thinking of the square as the outside function, and the x is the inside function, or in the other term, the y is the inside function. So I'm going to put parentheses so that we can think chain rule. Okay, so to differentiate the first term, thinking chain rule, right? We take the derivative of the outside, so that will now be raised to the first power. We leave the inside function alone. We just leave the inside alone. And now we differentiate the inside with respect to x, which would be dx over dx. And you guys can see that dx over dx, well, that's just going to be 1. Now here's the new part. So when we want to differentiate y squared with respect to x, let's think chain rule. So differentiate the outside, leave the inside alone, and then we multiply by the derivative of the inside with respect to x, which would be dy over dx. Okay, thinking chain rule. And we know that the derivative of a constant will just be 0. So let me clean this up. We'll have 2x times, oops, that's just going to be 2x, because that would be 2x times 1, plus 2y times dy over dx equals to 0. And now our goal is to find dy over dx. So we want to isolate dy over dx on one side of the equation, and I'm going to do that by subtracting 2x from each side. And then we can divide by 2y on each side of the equation to isolate dy over dx. So that'll give us negative x over y. Now this is different, right? Our derivative has both x and y in it. Normally, dy over dx, whenever we can define y explicitly in terms of x when we're differentiating a function, just has the x in it. But thinking back to what the graph of x squared plus y squared equals to 1 represents, right? The circle with a radius of 1. Actually, I'm going to redraw it down here. This is a circle with a radius of 1. You guys know points that lie on this circle from your knowledge of the unit circle. Do my best attempt at a circle. Not so good. Oh well. Okay, so you guys know different points that lie in the circle. For example, we know the point root 3 over 2 comma 1/2, and the point root 3 over 2 comma negative 1/2. Well, what if I wanted to find the equation of the tangent line or the slope of the tangent line at either of those points? They have the same x value, which before we would have just substituted x into our derivative, right, to allow us to find the slope of the tangent line. But this x value of root 3 over 2 corresponds to 2 different points now. So if I wanted to find the tangent line at root 3 over 2 comma 1/2, I would need to find the slope there, which we can see would be different than the slope at root 3 over 2 comma negative 1/2, right? They're going to be two different slopes, two different equations of the tangent line for two different points on the graph. So if we wanted to find, for example, the equation of the tangent line at root 3 over 2 comma 1/2, we need the slope, right? So the slope of the tangent line would be equal to the derivative evaluated at root 3 over 2 comma 1/2. That's the notation we're using to show that we're evaluating dy over dx at that point. I'm kind of running out of room, so I'm going to come below here. So it would be equal to negative, substituting root 3 over 2 in for x, over substituting 1/2 in for y. So that's equivalent to negative root 3 over 2 times 2 over 1. So just negative root 3. So that's the slope of the tangent line at this point. So we already know the point, we have the slope, so we could actually write the equation on the tangent line at that point is y minus 1/2 equals negative root 3 times x minus root 3 over 2. And I want to do one more basic example. You can see the example I have here. It's going to get a little more complicated where we're going to have to use additional rules. So let's do one more that's pretty basic. So let's add in a paper. Not paper, a page. Okay, so let's find dy over dx for let's find dy over dx for 3x squared plus 2y cubed equals to minus 4y plus 1. Okay, so we need to use implicit differentiation here. So I'm going to show that I'm taking the derivative with respect to x of each term. Now here I could actually pull the constant out front, and that goes back to when we first started talking about rules of differentiation. We're allowed to pull that constant out front and then just take the derivative of x squared. Again, we can pull the 2 out front. You could leave it in. It gets a little tricky though. I like to just always pull the constant out because it gets a little tricky if you are having to use like product rule. It's sometimes easier to just pull that constant out, but it's preference. Okay, so let's go from left to right to differentiate. So we would have 3 times the derivative of x squared, which will just be 2x. If you're thinking chain rule, it would be 2x times dx over dx. Well, dx over dx is just 1. Plus, next term, 2 times the derivative of y cubed with respect to x. So thinking chain rule. 3 times y squared times the derivative of y with respect to x. So dy over dx equals negative 4 times the derivative of y with respect to x plus 0. Derivative of a constant is just 0. So let's clean this up. We'll have 6x plus 6y squared times dy over dx equals negative 4 times dy over dx. So we're trying to find dy over dx. So our next step is going to be to get all of the terms that have dy over dx on one side of the equation and then all the other terms on the other. So I'm going to add 4 times dy over dx to each side of the equation and then subtract 6x from each side of the equation. So I'll have 6y squared times dy over dx plus 4 times dy over dx equals negative 6x. So now we have two terms on the left-hand side that have dy over dx. Notice each of these terms here, okay, we have dy over dx, so let's factor that dy over dx out. Oops, that's 6y squared plus 4. So now to finish isolating dy over dx, let's divide by the quantity 6y squared plus 4 on each side. So we had dy over dx equals to negative 6x over 6y squared plus 4. Finito. Done. That's dy over dx. So this equation would allow us to find the slope of the tangent line at any point that lies on the graph of that equation. Okay, so I'm going to make another video. I'm going to stop this one. I'm going to make another video with some of the more complicated examples.